Welcome, space lovers, to our Winter Solstice virtual star party. Along with EVscope users and space lovers from all across the globe, I'm getting ready to take you on some cosmic tours through, to start off, distant galaxies of our universe. Galaxies are sprawling systems of dust, gas, dark matter, and up to 1 trillion stars, all held together by gravity. They're beautiful, fascinating, and just may contain extraterrestrial life. We're going to learn about these spectacular systems and travel hundreds of millions of light years across the expanse of space and time. And I am joined by a few special guests today, including Professor Mike Maryfield, who joins us from the other part of the world. I'm here in Minnesota, and he's way over in the UK. Hi, Mike. It's nice to see you. Tell us, where are you located? Where are you right now?
I'm under a big cloud in the middle of Nottingham, which is pretty much in the middle of the UK.
Welcome, Mike. We can't wait to hear from you. We are also joined by Dan Peluso. He is a PhD student with the University of Southern Queensland, another distant part of our Earth, but also a researcher with the SETI Institute. And his research involves finding and characterizing exoplanets, as well as improving science and astronomy education across the planet. Welcome, Dan. And of course, I'm joined by my trusty sidekick, Val, who some of you may know. She is a Unistellar brand ambassador at the SETI Institute, and she is in charge of our Unistellar on the road, and you can see our trusty tour vehicle right behind her. So we'll be here, and we have a few other special guests joining us today. So we're going to start off with a conversation about galaxies. And with this, we have some hopefully delightful content. So I want to turn a pretty simple question over. I gave us a quick overview, but Dan, let's start with you. What is a galaxy?
The first time I ever heard of a galaxy was whenever I watched Star Wars when I was younger. And I remember in a galaxy far, far away. And I remember at the end of the Empire Strikes Back, giant blob like you can see on the screen, which is a spiral. So there are a collection of stars, gas, dust, planets, black holes, exotic matter, and actually mostly dark matter.
And we have some very interesting expertise in our guest, Mike. Mike, can you tell me, what are some interesting facts about galaxies that some of our viewers may not know or would be interested to know?
Wow, that's a tough one. Fascinating facts about galaxies. Firstly, there's an awful lot of them out there in the universe, billions of them. And they come in really all shapes and sizes. And in fact, it's quite hard to know quite where to draw the line in that, if you think a galaxy is just some stars bound together by their gravity, then actually, does a binary star, just two stars bound together, does that count? Or do you need, a large number? Do you need 1 million, 1,000, 100,000? So it's not particularly well-defined what a galaxy is. There's lots of things that are not well-defined about a galaxy. Another thing to think about is, of course, they don't actually have sharp edges. It's not like you go out in a galaxy and it suddenly stops. What happens as you go further and further out in the galaxy, it just gets fainter and fainter. And quite where the end of where one galaxy ends and the next begins is not really all that well-defined.
So they're so beautiful. Are there many different types of galaxies? Because I can see, they're all bright and massive, but they seem to be different shapes.
So there are different flavors of galaxies. There's 4 types. There's elliptical, there's unbarred, barred, spiral, and irregular. There's a really good analogy that you can think of the different shapes. If you took a handful of coins, just threw them up in the air, and looked at how the coins were in the air, you would see some coins that were flat, thin lines, and some that were circular and different angles. That's kind of what we see when we look up at the different galaxies.
So out of curiosity, Dan, why are galaxies among the preferred objects for our EVscope users to view?
Well, I think back to the backyard telescopes that I've tried to use whenever I was younger, and even whenever I was a little bit older, when most of the objects that you could look at were planets and the moon and sometimes star clusters. But looking at a galaxy, this seemed like something that only professional astronomers could do, or amateur astronomers with the most advanced telescopes at home. But the fact that we can take the EV scope out in your backyard, in your garden, or in your front yard, and just point this at an object such as the Whirlpool Galaxy M51 and see the beautiful spirals of hundreds of billions of stars, it's just an amazing thing. With just a couple presses of a button, anybody can look at a galaxy from their home.
Val, can you tell us a little bit about the Whirlpool Galaxy that we're looking at right now?
Yeah, sure. So this image is from Gary from St. George, Utah in the United States. The Whirlpool Galaxy is a spiral galaxy located about 23 million light years away. To give you an idea of size, it's about 75% the size of our Milky Way galaxy. It actually consists of two separate galaxies, a large spiral galaxy and its companion, a dwarf galaxy. They're a pair of interacting galaxies, meaning that their gravity affects each other so much that it's actually changing their shape. Eventually, they'll fully merge into a larger galaxy.
It's amazing. I think we have a series of images collected by EV scope users, and one of the most popular is, of course, the Andromeda Galaxy. Dan, can you tell us a little bit about our galactic neighbor, Andromeda?
Yeah, so Andromeda is actually one of my favorite galaxies. It's also known as M31. It's a catalog name, Messier 31. And it's actually named after a princess of Greek mythology. It means ruler of men. And an amazing thing about this is people have seen the Andromeda Galaxy for hundreds and thousands of years as this fuzzy patch in the sky. And it was a nebulous object, a nebula, a cloud of gas. And it wasn't until the 1920s when astronomer Edwin Hubble took his telescope at Mount Wilson Observatory in Los Angeles, California, and pointed his telescope at this cloud and discovered it wasn't just a cloud of gas and dust in our own galaxy, but another galaxy. It's one of the first other galaxies outside of our own galaxies that was discovered. It was thought before this that we might have been the only galaxy in the universe, that our entire universe was just our Milky Way galaxy. But then Edwin Hubble discovered that Andromeda was an entirely other galaxy, and that paved the way to us finding other galaxies that shows that we live in this universe of hundreds of billions of galaxies, each with hundreds of billions of stars. And it's just a really exciting thing. Some stats about it: it's 2.5 million light years away from Earth. It's about 220,000 light years across, twice as big as our own galaxy. There's over 1 trillion stars, which is a lot more stars than we have. We only have like 100 to 400 billion stars in our galaxy. And it's set on a collision course with our Milky Way galaxy, speeding at over 250,000 miles per hour. Don't worry, this isn't going to happen for another 4.5 billion years from now. And so don't worry about this crash either, because the stars are really far apart. So you're probably not going to have things exploding, but the matter and stars in the galaxy will be redistributed, and the galaxies will merge into a new type of galaxy about 5 billion years into the future.
So when you talk about galaxies, you're talking about things that are just shockingly far away. It's hard to even understand how far away they are. Does that mean that we're looking into the past when we see these galaxies?
Yes. So you don't have to travel 88 miles per hour in a DeLorean in order to travel back into time. In fact, I think I have my Back to the Future DeLorean right here. All you have to do is look through your EV scope. And when you look through your EV scope, you're looking at light. And light travels at the fastest that anything can travel in the universe. But it's traveling very, very long distances. So when light leaves the Andromeda Galaxy, for example, And Andromeda, as I said, is 2.5 million light years away. It took 2.5 million years for that light to leave the Andromeda Galaxy and make its way into our atmosphere through your EV scope optics and then into your eyeball. So you're looking at the Andromeda Galaxy, not as it is right now, but as it was 2.5 million years ago.
That is just shocking. We're seeing so many different shapes and types of galaxies. Why do they have different shapes? What causes that? Mike, could you tell us a little bit about that?
Yeah, and it's sort of, I guess it was one of the first things that people started thinking about when you know, mainly I guess when photography first came along and people were able to take these much more detailed views of what galaxies look like. But there was a lot of work went on as to classifying them and thinking about these sort of ordinary, you know, featureless looking elliptical galaxies versus the much prettier spiral galaxies. And actually it turns out that what might even be the intuitive thing to think about is what's really going on, that almost certainly if you leave a galaxy alone for a long period of time, then it's likely to form, you know, quite delicate structure, like the spiral galaxies. And in particular, if it's at all rotating, that'll make it rotate down into forming a disk. And so you'll end up with these disk structures, which means sometimes you'll see them as very thin if you see them edge on, sometimes they'll be round when you see them face on. But basically they're the ones that have sort of been left alone. But if you take a couple of those beautiful spiral structured galaxies and smash them into each other, you create this complete car crash, and there's bits of galaxy all over the place. And when things kind of settle down, you end up with one of these much more featureless elliptical galaxies. So it's possible for galaxies to change their type, and the main way that they change type is by crashing into each other, and that will take you from a spiral galaxy to an elliptical galaxy. So we now sort of understand quite a lot, not only what the types are, but actually how they're related to one another as well.
What type of galaxy is our own Milky Way galaxy? And, you know, are there things about it that are unique, or are we just another average galaxy?
It's a spiral galaxy, and as far as we can tell, it's a very ordinary spiral galaxy. Which one of the lessons we've kind of learned, we really should have learned by now in astronomy, is we're never as special as we thought we were, right? In that we used to think, the Earth was the center of the universe, and then we learned actually, no, it goes around the sun. We used to think, the sun's the only sun out there, but actually then you learn it's one of billions in the Milky Way. At some point, we thought the Milky Way was perhaps the only galaxy, but now we know there are billions of those out there as well. So every time we kind of learn, actually, we're really nothing very special. And it would be quite a surprise if the Milky Way turned out to be a peculiar galaxy in some way, because really everything we've learned about the universe is where we are in it is just a very normal kind of place. So it's hard to tell because we're in it, right? So it's actually hard to get that kind of perspective. You can't sort of see the wood for the trees, and so you can't actually really tell in great detail what sort of galaxy it is. But it's a spiral galaxy, and it probably looks like some of the ones that we've been looking at here.
So this is a fascinatingly named galaxy, the Superman Galaxy. And Val, I'm curious, could you tell us, why did this galaxy get such a fascinating name?
So yeah, it gets its nickname from the weird S-shaped appearance of its spiral arms. So this galaxy, along with our Milky Way galaxy, are classified as barred spiral galaxies, like you heard earlier. The bar structure in the center of these galaxies are actually found in about half of all of the spiral galaxies in our universe. So this galaxy is about 105 million light years away from us in the constellation Pegasus, and it extends about 100,000 light years across, which is similar to our own galaxy in length. And there's also evidence that this galaxy may have merged with another smaller galaxy, which gets its weird shape with the spiral arms.
Triangulum Galaxy. This one I have a special fondness for because it was the first galaxy that I was able to train my EV scope on, and then to see its colors and beautiful features come to life. It was just amazing. Can you tell us a little bit about the Triangulum Galaxy? It's kind of the star of the winter sky, is it not?
Yeah, definitely. This is one of the best times to see it. So yeah, this galaxy, along with the Andromeda, is one of our closest galactic neighbors. It's actually the third largest galaxy in our local group after the Milky Way galaxy and the Andromeda Galaxy. It's located 3 million light years away. slightly farther out than the Andromeda Galaxy, and it's smaller than our own galaxy, 60% of the size of our Milky Way, and it's home to about 40 billion stars.
So I'm curious, before we move on to our extra special guest, Mike Maryfield, do you have any favorite galaxies, Professor Maryfield? Anything that comes to mind in all your years of experience that really has stood out to you as being special?
I mean, look, I said, that at some level, there are different types of galaxy and we can classify them. But actually, every galaxy has its own story to tell. And each one, if you look into it, you'll find there's something interesting to say about every galaxy you can look at. So, for example, the Triangulum here, the M33, what's fascinating about this galaxy is one of the components we usually find in a galaxy, there's a disk of stars. There's usually this thing called the bulge, which is a kind of spheroidal, more circular component in the middle. The Triangulum Galaxy doesn't really have one. And so and again, we have to, if we want to understand everything about galaxies, we need to understand why do some galaxies have these central bulges and others don't. As I say, this is one that really doesn't have a central bulge. And the other interesting thing that goes with that is one of the other things that a lot of people already know about galaxies is that they have these massive black holes in the middle, supermassive black holes. The size of the supermassive black hole seems to be associated with the size of that kind of spheroidal component. And so because this doesn't actually have a spheroidal component, if anything, at best, it has a very small black hole in the middle of it. So there's something interesting to say about every galaxy. And actually, sometimes it's as you'll see in some of the galaxies I show a bit later on, sometimes it's the ones that look the least interesting turns out to have the most interesting stories to tell.
Well, that's actually a nice segue so that I can do my formal introduction with you. Dan and Val, thank you so much. I know that we'll see you both later to talk about things like nebulae and the Jupiter-Saturn conjunction and so much more. So thank you both. We'll talk shortly. And I do want to provide a formal introduction for Professor Mike Maryfield, who, as he mentioned, is joining us from the UK. Our special guest speaker is the co-host of Deep Sky Videos with 60 Symbols, which has over 70 million views. He's co-authored more than 140 different publications which have been cited 6,800 times. But I think perhaps the coolest thing, in my humble opinion, is his awesome lockdown astronomy Twitter feed, keeping us all entertained as we are sadly socially distancing. So you can find him and that at Astro Mike Mary. So welcome, Mike. I'm so glad that you are joining us today. Can you tell me just a little bit about your background, because it is truly fascinating?
Sure, happy to. So I'm professor of astronomy here in Nottingham at the University of Nottingham. I've been here for 20 years now. But actually, so my career, I started out in the UK. I'm originally from the UK, but I actually did my PhD in the States. Then I moved to Canada for a few years. The way an academic career often works, you do an undergraduate degree, a PhD, then you do these things called postdocs, where you have a kind of a short-term position. So I was in Toronto in Canada for a couple of years, and then I was in the UK, back into the UK in a city called Southampton for a few years at the university there. But then I moved to Nottingham, set up an astronomy group here. I now have, so there's nine faculty, probably including all the PhD students and postdocs, probably about 40 people in total. So it's a pretty sizable astronomy group now that we've built up over that 20 years that I've been here. So it's one of the things about academic careers is you kind of you end up traveling around quite a lot because you have to go where the jobs are. So I've done a reasonable amount of traveling, but I have sort of finally settled in one place now for a considerable period of time.
Well, thank you. I'm so glad that you're with us. I'm curious, what advice do you have for budding astronomers who may be joining and maybe this is their first star party? What tips do you have to get them started?
I guess enjoy it. Absolutely. It should be fun. If you're not enjoying it, stop doing it. But actually, once you start doing it, you'll find it's really hard to stop because it's very enjoyable to do. At least if you're from the UK, my other advice is wrap up warm because it's blooming chilly out there at the moment. And take the moments when you can, because as I say, in the UK, we spend a large fraction of our lives sitting under a cloud. So you've got a clear night and make the most of it. Get out there, enjoy the check out what you can see in the night sky. Although it's nice to have a really fancy telescope, you don't need one. You can see things with the naked eye. You can learn the planets, see them moving from night to night as they work their way around the sky, see the moon. But even a pair of binoculars, the moon can look spectacular in. So you don't need huge amounts of fancy kit. But obviously over time, if you really get into it, it's worth thinking about what you want in terms of a telescope and making sure you got whatever's right for you.
What about for people who may be more advanced astronomy hobbyists? Because I know with COVID and many people being locked down, telescopes are getting more use than ever before. What tips do you have for people who are looking for new ways to further their passion?
I guess the most important lesson I've learned is the best telescope is the one you actually use, right? So actually, if you end up with a telescope where it's so much faff to use, or you never actually bother to get it out, then that's a waste, right? And actually, the best telescope is the one that you can get out there and actually use. So as long as it's something you're comfortable using, you understand, you can get the best out of it, you enjoy using it. That's the important thing. So in terms of just the kit, it's got to be something that you will actually end up using, because otherwise the hobby's no fun, right? If it's actually, when it comes down to it and it's a clear night, I can't be bothered. That's no fun as a hobby. If you're only doing it because you feel you're obliged to do it. Whereas actually, if it's something you're enjoying doing, you're enjoying using the kit you've got, that's the most important thing, I think.
All right, well, let's dive into your presentation. So tell us, what have you got for us today, Professor Maryfield?
Okay, well, I sort of talked about some of this already in that where I'm from, University of Nottingham. I should mention the Science and Technology Facilities Council, which is kind of the funding body in the UK for astronomy. So some of the things, they fund quite a lot of my research, and at least one of the things I'm going to talk about, they're really the key agency that's dealing with it. The other two little logos up there, you already heard mention of the fact that I'm involved in these various videos, all produced by a guy called Brady Harron, who makes the most amazing YouTube videos. And so there are 60 symbols, which is mostly about physics, but there's some astronomy in there as well. Deep Sky Videos is the one that's most closely connected. We're working our way through the entire catalogue of Messier objects. And so we're making a video for every object in the Messier catalogue. We're almost there now. There's about 120, 130 objects. We're down to about a dozen left to do at this point. So we're working our way through that. The last little logo there, it's a little late for me to do my Christmas plug here, but I actually set up a company called Crystal Nebulae, which makes little glass sculptures of astronomical objects. So if you're short of a Christmas present, a late Christmas present, or you've got a birthday coming up sometime in 2021, check out Crystal Nebulae. You might find what you want there in terms of a nice astronomical object. As you've already heard, I do quite a lot on Twitter. I do what most people do on Twitter, which is I spend a lot of time arguing with people, but I actually also talk about astronomy from time to time on Twitter as well. And so you can check out what I do there. And the hashtag lockdown astronomy is all the stuff I've been doing since COVID came along, most of which has been with the EV scope. So I've been having a lot of fun with it, as you'll see in a minute. So I guess I should tell you a little bit about my astronomical career. When I was asked to give this chat, I was suggested I should show some pictures of me doing my day job. Well, actually, it's my night job, but you know what I mean. Actually, out there using some telescopes, and it turns out I have almost no pictures of me using large telescopes, using the telescopes I use in my professional career. Really, because when I get out there, I'm so busy focused. I'm so kind of focused on doing the work that I'm doing that I work all night, I sleep all day, and then I come home again. So the best pictures I could find, these are actually about 20 years old when we were actually commissioning a new instrument on the William Herschel telescope. We had a little bit more time because we were working during the day. And we took a few shots as we were going along to show this new instrument that we were putting on the back of the telescope. So here's the William Herschel telescope. It's a 4.2 meter diameter primary mirror here that collects the light. It's what's now called a small or medium-sized telescope. When I first started using it, it was known as a large telescope, but that's the nature of these things, that time moves on and telescopes get bigger. And so it's now what's known as I say, a small, medium-sized telescope. But it's one of the ones that I use kind of as a sort of workhorse for much of my career. I've lost count of the number of nights I've spent observing there. Typically, astronomers will go observing once or twice a year, and then they bring the data back and analyze it. And I've been doing that at the William Herschel telescope since the 1990s, I guess, so a fair while now.
Who names these telescopes? I'm very curious to know this because we've got very large telescopes and there seem to be not very descriptive for scientists who seem to be so precise about many things.
Yeah, and we used to be a bit more creative. One of the lessons, well, actually probably one of the lessons that was learned from the Hubble Space Telescope is it's probably not a good idea to give your telescope a nice name until you know that it works. Because when you may remember when the Hubble Space Telescope was first launched, there was a problem with the primary mirror and it was all a bit of a debacle. And poor old Edwin Hubble's name was mud for a while because, his name was associated with this telescope that didn't work. So quite a lot now, they tend to actually make sure the telescope works before they give it a nice name. But you're right. So, for example, the big telescopes that I use at the moment, the main telescopes, are things called the VLTs, which are the very large telescopes in Chile, run by the European Southern Observatory. And the one we're working on at the moment, let me show you the next slide here. The thing we're working on at the moment, having done the VLT, this is the ELT, which is the extremely large telescope. And I should say the picture at the top there is an artist's impression. We haven't built it yet. The picture at the bottom is the current state of it. Unfortunately, it was being built when COVID hit. Construction has kind of ground to a halt because they can't get the construction workers on site. But we're still quite hopeful that it will get finished sometime, in the middle of this decade. So we're looking probably 2026, 2027, I guess, but by the time it'll actually be finished. But this is the project. This is what I'm involved with for the Science and Technology Facilities Council, STFC. I'm kind of, I chair the committee, which is sort of overseeing the UK's contribution to this international project. It's a pretty expensive project. It's over a billion of whatever your favorite currency is, pounds, euros, dollars. So it's a big, expensive telescope project, but it will be, when it gets on the sky, it's going to be amazing. So in this case, remember I said the William Herschel telescope, the mirror is about 4 meters across. Here, the mirror that collects the light, so there's in the dome here, that's 39 meters across. So it's a factor of 10 bigger than the William Herschel telescope. So we really are building forever bigger and more dramatic telescopes, which really will allow us to see some of the faintest things. The real reason to build a bigger telescope is to collect more light. You can see fainter things with a bigger telescope. And so we'll be able to do things with the ELT that we can only dream of at the moment, because we'll just be collecting so much more light than we do at the moment. So that's sort of my professional side of what I get up to. Oh, I should actually say one other thing about naming telescopes. I should say this is again a project I've been involved with for a fair while. It's 39 meters in diameter. Our original ambition was even more ambitious. We wanted to build an optical telescope 100 meters in diameter, and that had the coolest name we've ever come up with for a telescope, which was called the OWL telescope, which stood for the Overwhelmingly Large Telescope. Unfortunately, it turned out that was just that little bit too ambitious. And so we've sort of scaled back our ambition a little bit, so that instead of building a 100-meter diameter telescope, it's a mere 39 meters in diameter. It's still going to be the largest telescope in the world when it's finished. It's going to be an amazing thing.
Wow, that is amazing. I can't wait until overwhelmingly large becomes a reality.
I think you're going to have to wait a while, because, this one, as I say, we've been working on this particular project for 20 years now. Once it's built, we're actually going to have to do something with it before we can justify an even bigger telescope. But there are 2 other large telescopes that are being built, one in Chile, one in Hawaii. So there are other large telescope projects on the way as well. Okay, so that was it for kind of the professional side of things. Let me scale down a bit. So here's a 39-meter telescope. Let me talk about my EV scope now. So it's coming down a little bit from 39 meters to 4.5 inches. But there it is, sat on my patio. I should say it has been absolutely wonderful to have it, because it arrived at exactly the right moment. Right? It actually arrived the day before the UK went into its first COVID lockdown. And so I was thinking I was going to be trapped at home with nothing to do except work, still do some work and what have you. But, most hobbies and things were not things I could do from home. The EV scope came along at just the time that allowed me to start looking at the sky. The other slightly embarrassing thing I have to admit is, as a professional astronomer, this is the first telescope I've ever owned. I've never actually had a telescope before. So I'd never really, had the opportunity to search the sky. That's partly because I've actually spent most of my life living in cities, and really, doing astronomy from a back garden in a really light polluted city with a traditional telescope is just really a bit soul destroying. there are clearly some challenges that I face in my wonderful patio observing facility here, which is the picture on the right sort of illustrates here. So here we are in the night time. There are a few things to notice. Firstly, I have a house in the way, a large part of the sky. Secondly, there are a large number of pretty tall trees around my garden, which my wife absolutely forbids me from chopping down. So I'm quite right too, I should say, but it really kind of restricts the amount of sky that I've got to look at. And all sorts of things like lining up telescopes. I can't see the pole star, for example, from most of my back garden. So actually being able to line up a telescope with the pole star, which is one of the classic ways of setting up a telescope, you just can't do. And the other thing that I struggle with, you can also see in this picture, which is because I'm in the UK, there are clouds quite a lot of the time, which just means that you need to be able to snatch those half hours when you finally actually get a clear half hour. And that's again why I really like the EV scope, because it's one of those things you can set it up so quickly that actually if you think it's going to be clear for the next half hour, it's worth getting it out, because you're only going to spend 5 minutes setting it up, and then you've got 25 minutes to observe before the clouds come back again. So I've had a complete blast with it. And in fact, all the pictures I'm going to show after this are just pictures that I've been taking of galaxies with it. So let me show you some of the pictures. So let's start with a couple we've already seen, actually. So this is my go at Messier. There are some galaxies you just have to have a go at, right? And just because they're the kind of classic galaxies, and you've just got to take their pictures. So here's Messier 51, one of those must-see galaxies. As you can see, it's a beautiful spiral. It's what's called a grand design spiral, in that you can actually see it's got these beautiful spiral arms where you can trace them in this beautifully symmetric pattern. Looks like, I mean, so its other name is the Whirlpool Galaxy, and it really does look like a whirlpool because it's got these beautiful spiral arms. The other interesting thing about it is it has this little companion, and these things are probably not unrelated, in that it seems that the most of the time where you find these beautiful grand design spiral structures, there's usually something which is stirring them up. So we sort of understand spiral structure reasonably well. It's a sort of wave that's traveling around the galaxy. Rather like a sound wave, in that it's compressing and expanding the gas as it goes round. And where you see the spiral arms is where the gas is most compressed, and stars are forming because the gas has been squashed, which is making them start collapsing into stars. So you sort of see the spiral arms lighting up with these new stars forming. But the beautiful grand design spirals, I mean, you can sort of see, right, that the spiral arm seems to actually join on to the little companion here. And so they're really clearly quite closely related to one another. But this is the classic one. This is, I mean, you know, this was probably the first galaxy, one of the first galaxies I actually took a look at. Yeah, you can see the date here. So I started with the telescope in March, and this is April. So it's quite early on while I was playing with the telescope. Absolutely beautiful, and a spectacular thing to look at.
Why do so many of the objects we're looking at have the name Messier attached to it? Can you give us some background?
So Charles Messier was a 18th century French astronomer who wasn't interested in galaxies at all. Of course, they didn't know galaxies existed then, but he wasn't actually interested in these, this would have been called a spiral nebula, right? He was actually interested in comets. And he was a bit irritated because there were lots of fuzzy things. So he was trying to find comets, and he kept thinking he'd found another comet, and it turned out to be just a galaxy from his perspective, or just a cluster of stars, or just a planetary nebula, or some of the other things you're going to hear about during the course of the rest of these sessions. And so he just wanted to compile a catalogue of things that weren't comets, so he wouldn't get fooled into thinking he discovered another comet. So it's a slightly strange thing, because, as I say, they were just his, you know, as far as he was concerned, he was compiling a catalogue of irritants, but actually they're some of the most beautiful objects in the sky, because they are, you know, they're the big fuzzy things in the sky, which tend to be the most interesting things to look at. Because of that, it's actually very different from almost every other astronomy catalogue, in that it's very heterogeneous. It's got lots of different things in it. As I say, there are galaxies like this, there are planetary nebulae, exploding stars, there are clusters of stars within our own Milky Way, there are gas clouds in the Milky Way. There are one or two where he just messed up completely, and it turns out, you know, so one of them, for example, is a binary star. It's just two stars, which for some reason he thought was a fuzzy object. So some of them turn out to be completely sort of irrelevant, spurious things. But the nice thing about it, like when we came to make this set of videos, because they're all different, because there's so many different things there, it's a really great thing to be making videos about, because there's, you know, there's all sorts of different things going on in different objects. But it is quite weird as an astronomical catalogue. Okay, so that was Messier 51. Here's another of Messier's objects, one we've also already seen, Messier 31. I actually had to go at making a little bit of a mosaic, so I made several pointings of it because it doesn't actually fit within, it's so big on the sky that it doesn't actually fit within the field of view of the EV scope. It's actually about 5 degrees across, something like that, so about 10 times the size of the full moon. As I said earlier, one of the problems with the galaxies, they don't actually have sharp edges. They just get fainter and fainter. So quite how big it is a slightly not a particularly well-defined thing to say. But as you can see, so the EV scope has a field of view which is about the size of the full moon. So the full moon would fit in one of these just about. And you can see even the bits that I've been able to see from my not very dark back garden span, about 3 or 4 full moons across. So a beautiful object. When I have another clear night and a bit more time, I'll go back and actually probably fill in some of the gaps here because it'd be quite nice to make a really big mosaic of the whole thing. But it's already looking quite spectacular even there. So again, another of Messier's objects is a Messier 31. I think the next one is probably a Messier object too. Yeah. Okay. So this is Messier 61, another beautiful spiral galaxy. It's a little bit further away. I'm gonna have to look at how far away it actually is. About 50 million light years away, this one. So again, beautiful fit, and this is one of these ones that has a bar in the middle. You can probably see there's this sort of rectangular structure, as was mentioned a bit earlier on. About a third to a half of spiral galaxies have these rectangular bar structures in the middle. But the reason I wanted to observe it is I had just seen a report that said there'd been a supernova had gone off in this galaxy. So I thought I'd have a go at looking for it. And there, the red circle here I've added, it's not there on the sky for you, but the little dot here is actually the supernova that exploded in the spring in about April time, May time, I think it was, yeah, early May it exploded. So I was able to go out there and take a picture of it and actually follow it over a few nights and see its brightness changing as time went on. It's not often when you're looking at galaxies that things change, right? Because galaxies, they rotate. It takes hundreds of millions of years for a galaxy like this to rotate. So actually you don't see anything move and anything change very much. But supernovae, exploding stars, are one of those cases where you do actually see things change.
And tell us about the chart that we're looking at.
Yeah, so this was put together by an amateur astronomer, a guy called Ian Slepian. If you just search for his name, you'll find, Google for it, you'll find his name. You'll find this chart on the right here. This is just showing how the brightness of this supernova changed with time. It's too small to see. I mean, even I'm struggling a little bit, but basically the time here runs from May through to August. So the axis along here is time from May on the left to August on the right. And then up on the axis here is how bright it is. And it's in these weird units that astronomers insist on using called magnitudes, which are a kind of strange back to front scale and a logarithmic scale. But what it really shows is that from that period, from May to August, the thing varied in brightness by about a factor of 10 in brightness. So it faded away. So when a supernova explodes, so this is a massive star that had just reached the end of its life. And at the end of its life, it kind of collapses down under its own weight, and then it sort of bounces back out again. And what you're seeing here is the explosion, the bounce as it flies, sends parts of itself flying out into space. And so you're seeing that explosion, but of course, as with any explosion, it kind of fades over time. And that's what you're seeing here, is that the explosion started very bright, but it's getting fainter and fainter as time goes on. I guess the other thing to say about these supernovae is this is where a lot of the heavy elements come from. I mean, some of them are made in other ways, but a lot of the heavy elements are the things we're made of. So if you're wearing I've got a gold wedding ring on, for example, quite a lot of the gold in the universe would have been made in an exploding star like this. Many of the heavy elements, heavier than iron, get made in supernovae. So these are sort of the birthplaces of some of the material that we've used, that that's all around us in the Earth today, that were made in historic supernovae that occurred many millennia ago. Well, actually longer than that, many millions of years ago. So you're seeing kind of the birth of heavy elements when you see a supernova like this. So that's Messier 61. What else was I going to talk about? Okay, so this is I included this one. This is a galaxy called NGC 7217. So NGC means it comes from the New General Catalogue. And the trouble with calling anything new is at the time when you call it new, it was new. But of course, now it isn't new any longer. But it's the New General Catalogue. It's mostly galaxies. It's got some star clusters in it as well. It sort of followed on from Messier's work. So the Herschels, for example, famous astronomers, were responsible for collecting a lot of the information for the NGC, and lots of other astronomers contributed. But this is a collection mostly of galaxies. As you can see, this is towards the end of the catalogue, and it's number 7,000 and something. So there's about 7,500 objects in the NGC, many more than in Messier's catalogue. But this is a particular favourite galaxy of mine. And it goes back to what I was talking about at the beginning, that sometimes galaxies that look completely innocuous have an interesting story to tell. So here it is. Here's my, let's get me pointed to work. There's the galaxy. Here's a kind of a blow up of the image. I just enhanced it a little bit and blew it up a little bit. It looks pretty dull, right? It doesn't have that beautiful grand design spiral structure. If you look really closely, you might be able to see a little bit of spiral structure. So at the one end, we have this stuff called grand design spiral structure. At the other end, we have what's referred to as flocculent spiral structure. So little tiny bits of spiral structure. And so that's what this contains. It's not particularly special, but we studied the motion. So this is work that I did with a colleague, Konrad Kuiken, many years ago, where we looked at the motions of the stars in this galaxy, and we were looking at the Doppler shift in the light. So just as sound has a Doppler shift, if you hear a siren of a fire engine, when it's coming towards you, it's higher pitch. When it's going away from you, it's lower pitch. It's the same with light, but in light, the equivalent of pitch is the color of the light. And the light gets shifted slightly towards the blue end of the spectrum when the stars are coming towards you, slightly towards the red end when they're going away from you. So we can actually see the rotation of the galaxy by seeing which bits are coming towards us, which bits are going away from us. This galaxy is really peculiar because about sort of 2/3 to 3/4 of the stars are rotating in one direction, but 1/4 of them are going around in the opposite direction. It's still not really well understood how you make systems like this. It's probably something to do with two systems merging together. But in this case, they haven't merged to produce one of those featureless elliptical galaxies. It's still a little bit of a spiral galaxy. And so it must have been a much more gentle merger process. They're quite rare. There's probably about a dozen or so systems like this that are known now. But this was one of the first that was discovered, where we found that actually not all the stars go round in the same direction. So it's not kind of that usual sort of swirling picture of all the stars going one way. Some of them are actually going in the opposite direction. So that's that guy. What else was I going to talk about? Then I got really interested to know quite how far I could push things and how far away I could see things. So here's a nice picture. This is a nice edge-on spiral galaxy, NGC 3079, so from that same catalogue. But actually, that wasn't really what I was after. What I was after was this. You can probably just about see it, maybe in the middle there. But again, maybe the blow-up will help. So this is a blow-up of that little bit of the image there. So that's these three stars here, or these three stars here. But I was interested in these two little dots in the middle here. And just to show you there really is something there, there's a Hubble Space Telescope picture of the same thing. And actually you can see the star there and those two objects, the star and these two objects. So we can pick up the same kind of things that even the Hubble Space Telescope see. But the fascinating thing, these two dots aren't two separate objects. They're one object. And the one object they are is a thing called a quasar, which is a very, very bright, very distant object. And the reason it's very bright is because material is falling onto a massive black hole in the middle of the galaxy, producing incredibly energetic processes that make it incredibly bright, so that central part of the galaxy actually outshines the whole of the rest of the galaxy. So that's the quasar. That's an amazing piece of physics in itself. But then the other thing that's going on is that maybe you can see from the Hubble Space Telescope picture, there's a whole bunch of galaxies there as well. Like all these little dots you can see are galaxies. That's because there's a cluster of galaxies. And they're nothing to do with the quasar. They just happen to be along the line of sight. They're between us and the quasar. And so you've got the quasar in the background, then this cluster of galaxies, then us. And what that cluster of galaxies is doing is the gravity of it is bending the light from the quasar, because gravity affects everything, including light. So the path of light is being bent. And what it's doing is exactly the same thing as a magnifying glass does, right? A lens does, that a lens bends the path of light. So this is what's known as a gravitational lens. So it was a phenomenon that was predicted by an astronomer back in the 1930s called Fritz Zwicky, who said that actually maybe we ought to be, if there are massive clusters of galaxies out there, we ought to be able to see this phenomenon. That was the 1930s. This was the first one that was discovered in the late 1970s. So it was a long time before any of them were discovered. There's now a fair number of them known. But I really like this because this is the most amazing piece of physics that I can see from a back garden in the suburbs of Nottingham. Right? I can see something. This is something where we were talking about how long it takes the light to get to us. And so for the Andromeda Galaxy, we're hearing it's a couple of million years. Right? This light has taken 10 billion years to get here. Okay, so we're seeing this as it was 10 billion years ago. The light has taken 10 billion years to get all the way from that distant quasar to my back garden to fall into the UV scope for me to take a picture. Along the way, and remember, it was produced in this amazing way of very energetic processes of things falling into a supermassive black hole. But along the way, it's encountered this cluster of galaxies, and so its light has been bent, and it's been effectively, the light kind of splits into two, in that one part of the light goes one way around the cluster and the other part goes the other way around. And so the net effect of that is we end up seeing two images of this quasar. So we're seeing, and this is something that's predicted by general relativity. It's a sort of test of general relativity that says that actually the path of light should be bent. So the amount of physics that's going on just in this one picture in my back garden, it really makes me happy to see. And again, it's probably the least inspiring picture, isn't it, right? Two little dots, right? But actually, it's two little dots that are telling us something truly amazing about the universe. Mm-hmm. So let's rattle on a few more pictures while we're here. I got really interested to see quite how faint we could go. And so again, this is another really challenging object. It's a thing called the mice. Done something bad to my screen. There we go. That's fixed again. So this is the object. And again, here's a nice little blow up of it. And here again is how the experts with the Hubble Space Telescope, they get a better picture. There's no denying it. But actually, I'm quite chuffed with how well you can do from the back garden. So this is a pair of galaxies which are really closely interacting with each other. They're in the process of colliding with one another. That tail that you can see from one of them, right, that's stretching out here, that's actually material that's kind of being ripped off. It's what's called a tidal tail, that the pull of gravity on the different sides of the galaxy are so different that it's stretching the whole galaxy out. And so this tidal tail is kind of this effect that you get where you have this strong gravitational interaction between galaxies that literally rip them to pieces. So these are two galaxies which probably started as spiral galaxies, but they're well on their way to forming a single elliptical galaxy, merging together into an elliptical galaxy. So that was a really fun one. And then I really decided I'd push my luck a little bit further. So this is a really challenging object to take a look at, a thing called Seafoot Sextet. So again, here's the picture from the EV scope on the left, and here's the Hubble Space Telescope image of the same thing. And again, you can see it does quite a remarkable job. It's something of a misnomer. So it's called Seafoot Sextet because it was discovered by a guy called Carl Seafoot in the 1950s. And sextet because it looks like there are 6 objects here. 1, 2, 3, 4, 5, 6. It turns out there aren't really 6 objects together. So this thing on the left here actually turns out to be a part of this galaxy here. And it's again one of these tidal tail things. The interactions between these objects is ripping this galaxy to pieces. And you can see this is kind of some of the debris that's getting ripped off it. So these are actually one object. And then it turns out this guy here, this little blip in the middle, it's rather clear on the Hubble Space Telescope picture, it's actually a spiral galaxy, which is nothing to do with this group at all. It's in the background. It's at a completely different distance. It's much further away. So it's an unrelated galaxy along the line of sight. So there are actually 1, 2, 3, 4 galaxies which really are interacting with one another. If you came back in a few billion years' time, you'd find they'd all merge together to form a single giant elliptical galaxy. So this is kind of, again, that kind of merger process where you can turn spiral galaxies into elliptical galaxies, but in a grand scale here that we're actually smashing 4 galaxies together instead of 2.
And it's extremely misleading because these look like they're close together, but in reality, how much space and time are we observing in a single image?
So the main ones really are very close together. They are but essentially at the same distance away from us. But that little guy here is, I think it's about 10 times further away. So actually it's nothing to do with this group of galaxies at all. It just happens to lie. And it's one of the frustrations in astronomy is you only ever get a 2-dimensional picture, right? And actually it's hard to learn about that 3rd dimension. There are tricks that astronomers use. We use the expansion of the universe and this thing called Hubble's law, which essentially tells us how far away things are. But they are these indirect tricks. It's hard to get a kind of a 3D view of even what a single galaxy looks like. I mean, we talked about spiral galaxies and said they're thin disks. One of the main ways we know that they're thin disks is because we see some of them edge on, so they look like, just a single slice in the sky, and others that are round. But you never get to see both, right? Either it's that way round or it's that way round. And so it's a sort of indirect, trying to figure out the 3-dimensional structure of any single galaxy. It's always done in this sort of indirect inference way. So you're right. It's, that third dimension is sort of lacking to us, and it's hard to sometimes disentangle what that third dimension is, as indeed in this case, where one of the galaxies is nothing at all to do with the others at all. So there's that guy.
How do astronomers know that what you're looking at aren't in fact galaxies that are closely concentrated, but that one is separate from the others? What types of tools or techniques do you use to determine this?
So in this case, there's this fairly simple thing. So when Hubble figured out that the universe was expanding, that there were these, as we heard at the beginning, that there are other galaxies out there, the other thing that he found out was that how far away they are is related to how fast they're receding from us. And again, we can use this Doppler shift effect to measure how fast galaxies are running away from us. Turns out almost all the galaxies, with the exception of a few like the Andromeda Galaxy, most of them are flying away from us just due to the expansion of the universe. Everything's flying apart from everything else. But as with any kind of explosion, the bits that are traveling fastest get furthest. And so actually the galaxies that are traveling fastest away from us are the ones that are furthest away. So by measuring this Doppler shift, you're essentially measuring how fast it's traveling away from us, which is telling us how far it is away from us. And the relationship between the two is this very simple relationship that they're kind of proportional to each other. If a galaxy is traveling away from us 3 times as fast, it's 3 times further away. And that's this thing called the Hubble law. So by just measuring the speed at which these galaxies are going away from us, this whole group are all traveling at more or less the same speed, which tells us they're probably at more or less the same distance, and they're all gravitationally bound together. Whereas this guy is traveling away from us very much faster, and therefore actually, it's very much further away. Okay, I've got just a couple more. Have I got time for a couple more?
Yeah.
Okay, do a couple more. All right. So what was I going to talk about next? Okay, so this is a really fun one. This is coming back to nearby galaxies again, but again, things which are hard to see. I like making life hard for myself for some reason. So this is a pair of galaxies called Mafe1 and Mafe2. And they're so cool because they were discovered by a guy called Paolo Mafe, an Italian astronomer, and they were only discovered in the late 1960s. And the reason why they were so late in being discovered isn't because they were a long way away, it's because they're really hard to see. And in fact, you can see part of why they're hard to see from the pictures. There are many, many stars in these images, right? All the previous images I showed you have many fewer stars in them. That's because these are right in the plane of the Milky Way. So the Milky Way is this galaxy that we're in, and because we're in it, we see as this plane of light across the sky. And so when we're looking at these galaxies, we're kind of looking through our own galaxy. And that's why we see lots and lots of stars. But the more troubling part, the why they're really hard to spot, is because as well as the stars, galaxies contain this stuff called dust. It's something of a misnomer in that it's not like, the dust that you get if you don't vacuum around the house is sort of dead house mites and all sorts of really disgusting things that you don't want to think about. Right? The dust, when astronomers talk about dust, they're referring to stuff that's much more like smoke. It's like soot or smoke. It's very fine particles, but just like smoke, you can't see through it. And there's lots of it's produced by stars. Stars produce these kind of little granules of carbon and so on, which really are kind of sooty, smoky material. And so in the plane of our galaxy, there's this dust layer of sooty material. And we're looking through, because this stuff is very close to the plane of our galaxy, we're looking through a whole load of this sooty material. So in this case, about something like 97% of the light gets absorbed by that sooty material. So only 2 or 3% of it gets through. That's why they're really hard to spot. And in fact, they were only discovered when Paolo Mafe was playing around with infrared astronomy, was moving to longer wavelengths, so out of the optical part of the spectrum. Because the nice thing about infrared light is it goes through this soot, right? The soot is very good at absorbing optical light, but infrared light just travels straight through it. So he could see through the smoke, just like firefighters use infrared goggles so they can see through the smoke in the fire. It's the same thing here. By doing infrared astronomy, he was able to find them. And so it was they're really quite challenging to spot. But this guy on the left here, Mafe1, is actually a giant elliptical galaxy. It's about the same size as the Milky Way. It contains about the same number of stars as the Milky Way. And it's very nearby. It's one of our nearest neighbors. If we weren't viewing it through all this murk, it would be one of the 10 brightest galaxies in the sky. But because we end up seeing it through all this junk between us and it, it's actually pretty hard to spot. And it's actually a member of a thing that's now called the Mafe group, in the Mafe1, Mafe2, and there's a couple of other galaxies in it. It's the closest group of galaxies. So the Andromeda Galaxy, the Triangulum Galaxy, the Milky Way, and a bunch of smaller galaxies form this thing called the local group, which is our closest group of galaxies. The Mafe group is the next closest group of galaxies. It's about 10 million light years away. So it's actually, again, in sort of astronomical terms, our near neighbor. But we never get to see it because, as I say, we're viewing it through all this junk it just happens to be in the wrong part of the sky to actually take a look at it. So
that was about such shocking distances. By the way, how do you wrap your brain around the huge distances that exist in the world of astronomy?
It's an interesting thing in that actually in my everyday work, they don't freak me out at all because I deal with them all the time and they're just numbers and I'm used to it. And I'm, because you're thinking in those scales, 10 million light years doesn't sound very far, right? Because actually I'm used to dealing with things which are 100 billion or 1,000 million light years away. So 10 million light years, and in that kind of way, I have it professionally calibrated, and that's a nearby galaxy. But when I start talking about it in situations like this, that's when I kind of take that step back and think that's ridiculous, right? That's, even this near neighbor, the light's taken, light travels ridiculously fast, right? It's the fastest thing there is. And even traveling at this fastest speed that there is, it still takes 10 million years for the light from this nearby galaxy to get to us. So you're right. I mean, the distances are quite ridiculous. But it really is only when I start talking about them like this that you kind of take that moment to think that's truly amazing numbers that you get out of this kind of thing.
Why is there so much study of things that are so distant? I mean, the likelihood that we could ever receive a signal from them or reach these places is almost, non-existent. So why do we study these distant galaxies?
So there's a couple of reasons. One is that some galaxies types are pretty rare, and that means that the closest example, just by chance, is likely to be quite a long way away, right? There's not that you'd have to be very lucky for a particular rare kind of galaxy for it to be right next door. And so for some kinds of galaxies, we absolutely have to look quite a long way away just to find, if you want a really massive galaxy, for example, they're quite rare. And so maybe you have to go 50 million light years to find one. So the rarer things are, the further you typically have to go to find one. The other thing is slightly subtler, which is that, as you heard at the beginning, these things are time machines, right? In that when you're looking at something, you're seeing it as it was in the past. Now, in astronomical terms, 10 million light years, so 10 million years isn't very interesting because nothing much happens typically in 10 million years in astronomy. But if you look to a galaxy which is maybe 5 billion light years away, so that means the light's taken 5 billion years to get to us. That means you're kind of peering back to almost through half the history of the universe. And galaxies look different in the past, right? They had to start, if galaxies are big today, they almost certainly started small, right? And they built up over time. And so we can actually see directly how galaxies are evolving by comparing those that we see very close to us to those that we see a very large distance away. So it's a tool that we can actually use for studying how the universe has evolved by comparing the nearby examples of things to the very distant examples of things. So there are sort of good scientific reasons, but you're right. To be honest, we're never going to get 10 billion light years, right? I mean, 10 million light years is already a ridiculously large distance to even think about traveling. But there are sort of good astronomical reasons why you might want to study the ones which are a bit further away. All right, I have one last one to show you. Let me just show you this one. I'm only showing you this one because this is the one I happened to observe last week. So clear night last week, had only about half an hour clear, but it was enough time to get the telescope out and have a look at this. Again, it's one of these ones from this new general catalogue, number 1530 in it. There's the original image, and here I've kind of blown it up a bit. And I really like this galaxy because it's a beautiful spiral galaxy. You can see the spiral arms, but actually this is one that's got one of these very strong bar features in it. So it's got this rectangular structure in the middle. The spiral arms are clearly associated with it in that they seem to join on to the ends of the bar. And then the last thing you may be able to see is, you remember I talked about this sooty material, the dust that astronomers see in galaxies. This has dust lanes, but they're actually in the bar, and you can maybe see that there's a dark bit up here and there's a dark bit down here. So you've got this bar structure in the middle, and then these dust lanes which are kind of offset within that central bar. And that's telling us where, so there's gas orbiting around within that central bar, and the gas orbits are really distorted by the gravitational pull of the bar. And in some places, they end up being really squashed together, and you end up creating effectively supersonic shock waves. And where you have these shock waves, you end up having, just as with a sonic boom, where you end up with the material getting very compressed together. It's the same story with this. There's kind of a galactic scale sonic boom going on with all that material getting very squashed together. And where the material squashed together, that squashes together all this sooty, dusty material as well, which obscures our view of it. So it's a beautiful study that we can actually understand the motions of stars within this galaxy and the motions of the gas within this galaxy by studying things like these dust lane features, which tell us about how that gas is orbiting around and where it's getting all that gas is getting squashed together to form these beautiful dust lanes. So that was a fun one, just from a kind of an astrophysics-y point of view, but it was just a random galaxy I picked. As you can tell, so that's number 1,530. As I say, the new general catalog goes up to 7,000 and something. So there are a whole lot of galaxies to look at. I haven't hardly scratched the surface so far. Even from the limited bit of sky that I can see from my back garden, there are still thousands of more to look at. And I really look forward to having a look at a few more of them.
Well, this is great. Thank you, Professor Maryfield, from joining us deep into this winter solstice evening from way over in the UK. We've appreciated learning about galaxies and seeing your observations. So thank you so much. And clear skies to you and everyone in the UK.
Thank you. It'll make a nice change.
Good luck and best wishes.
It's been a pleasure.
All right, so now we're going to move along because we're not just going to learn about galaxies, but what just might be inside of these galaxies. So something interesting to know, not a single confirmed planet outside the solar system had been detected before the year 1992. But remarkably, we now know that thousands of such exoplanets exist, and we have studied many of them in actually surprising detail. And so I am joined, sorry about that, Mike. I'm joined by Dr. Tom Esposito, who has a PhD in astronomy and is an astronomer at the SETI Institute as well as UC Berkeley. And for those of you who are not familiar, the SETI Institute is the scientific partner of the Unistellar network of citizen astronomers. So Tom investigates what kind of planetary systems exist in our galactic neighborhood and how those collections of planets, asteroids, comets, dust, and gas change over time. So welcome, Tom. Can you tell us just a little bit more about your studies and what you're hoping to learn through your studies?
Sure. Yeah, so, exoplanets is kind of one of the hottest things in astronomy right now. And it's also one of the things I think that captures people's imaginations the most in science in general, really. And there's a few things that we're trying to learn. So one thing is, kind of very closely tied to SETI's mission. We know that life on Earth lives on a planet, right? Earth is a planet. And so if we're going to find life somewhere else in the universe, somewhere else in our galaxy, one good place to start is to look for life on other planets. And in order to do that, we need to know where those planets are and, what they're like. And so really we want to know, part of what I want to do with my work is find out, where planets are, how different planetary systems, how other solar systems are made, and how they're kind of arranged in order to, answer questions like, is our solar system common or rare? Are we special or not? And similar questions like that.
And later today, we'll get to that important question. Is there really a galactic federation? And if so, how do we join?
No comment.
All right, so let's watch this video a little bit about exoplanets. I know the sound was a little loud earlier, so hopefully we'll get a good show this time around. So Tom, what do we know about exoplanets today? Can you tell us a little bit?
Yeah, well, I should first define them, I think. So exoplanet, you can break down the name into two parts. So there's the first part, exo, and that just means outside or beyond. And in this case, we mean outside of our solar system. And then there's the planet part, which I think we kind of all have an intuitive sense for, what a plain old planet is, just from Earth. It's a big ball of rock and metal and liquid and gas that, but there's three kind of major technical requirements in order to define something as a planet. And so one, it has to orbit a star or stars, right? So Earth goes around the sun. That's a planet, and that's one thing that separates planets from moons, for example. So a moon directly orbits its planet. It doesn't directly orbit the star. Number two, the planet has to be massive enough. It has to have enough material in it and be dense enough that its own gravity shapes it into a kind of a round sphere shape. And then three, it has to be massive enough and have enough gravity that it either scoops up or flings away the material nearby in its orbit, and so it kind of clears out its own space nearby. And that was one of that third one is kind of what demoted Pluto, so that it wasn't considered a major planet anymore. And so what we know about exoplanets today, well, kind of maybe the main thing is that we know that they're common. There are current estimates right now that on average, there are about between 1 or maybe up to 10 planets per star in the Milky Way galaxy. And there's about 100 billion stars in the Milky Way. So that's, 100, what, I don't know, carry the 1, divide by 10. There's about 100 billion to 1 trillion planets in our galaxy alone. And then there's hundreds of billions of galaxies out there. So there's a lot of planets. And we're seeing some of these images. There's lots of different ways we can detect and find those planets. We can do it with an image like this, where we actually see the light from the planet directly by basically pointing big telescopes with very sophisticated digital cameras on them at those planets. Or we can detect them indirectly, like we're showing here with this transit method, where we measure changes in the light from the star that the planet orbits. And through all of these different techniques so far, since, as you mentioned, 1992 was the first detection of any kind of exoplanet. The first detection of a planet around a sun-like star was in 1995. And since then, we've detected over 4,300 exoplanets in our local neighborhood of the galaxy. A lot of those came from NASA's Kepler mission, which ran from about 2010 to 2018. And we have about almost 2,500 more candidates that are just waiting to be kind of vetted and approved as being real planets. A lot of those come from NASA's current test mission. And so some of the pictures that we're seeing here, we know that there's lots of different types of planets, and they come in all different sizes and flavors, including some that we don't have in our solar system. So there's super Earths, these planets that are a few times larger than the Earth, with a rocky surface, and they have a thin atmosphere, kind of like the Earth, but they're bigger. Some of the people listening might have heard that Saturn would float in a bathtub if you could find a big enough bathtub. But we've actually found planets that are even less dense than that. They're lighter, they're fluffier. They're actually the same density as cotton candy. And so they're super fluffy, these so-called super puffs. And then there's these hot Jupiters, Jupiter-sized planets. Jupiter is the biggest planet in our solar system. They are extremely hot. They're close to their star, so they're thousands of degrees in temperature on their surface. And as we're developing methods and technology, we're finding more and more types of planets and more of them out there. Whitney, you're muted. Sorry.
That.
There.
Thank you, Tom. What type of exoplanets do we study with the EV scope? Because I know that there are many different types of scientific devices. For anyone who is not yet familiar with the EV scope, it is a smart telescope, and it allows people throughout the world to come together because these devices are the same. So we can aggregate the data and the observations and learn about certain types of exoplanets. So what types of exoplanets do you study?
So with the EV scope, so far, right now, we've been detecting our exoplanets through this transit method. And so we showed a couple of movies illustrating this earlier, but Whitney, maybe now you can play a couple of those again. And an exoplanet transit is when the exoplanet, moving along in its orbit, passes across our line of sight to its host star. And when it does this, it's like a solar eclipse, when the moon casts a shadow on the Earth. So we see, it's about to happen now, we see a small dip in the brightness of that exoplanet star. And that dip is small. It's only a few percent or much less. And this is the smoking gun that the planet's there. Even though we're not measuring any light directly from the planet itself. We're only seeing the starlight. And so this is similar to back in, I think, 2012. Many people watched the Venus transit of the sun, where you saw a tiny little black dot move across the face of the bright circle of the sun. And this is basically the same thing. And so you can see here on the left and the right, we have two different sized planets that are orbiting the same star. And you can see on the left, the bigger planet creates a larger dip in the star's brightness than the smaller planet on the right. And so with the EV scope, we're seeing these large, kind of the largest planets we can, these Jupiter-sized planets Jupiter is about 10 times larger across than the Earth. And so that Jupiter creates about a 1% dip in the star's light. Actually that's if it's going around the sun. Most stars are actually smaller than the sun, so sometimes it might create a 2 or 3% dip. But these are we have to make pretty precise measurements to do this. And luckily, with the EV scope, we can. And so with a single EV scope, we've already, members of the Unistellar network have already detected over 20 exoplanets with this method. And they tend to be these hot Jupiters they're large, they orbit close to their star, and so they transit very often. So they're ones we can see the most frequently.
So why are we utilizing the EV scopes to study exoplanets when we have something like the Hubble Space Telescope out there? Can these devices really work together to achieve a common goal?
Yeah, so that's a good question. I mean, we have lots of professional tools in astronomy, lots of telescopes, though we could always use more. Write your congressman or congresswoman. But really, what needs to be done is we actually are at the point where we're finding so many exoplanet candidates. So NASA's TESS mission, the Transiting Exoplanet Survey Satellite, Survey Satellite, is in orbit around the Earth right now, and it's finding thousands of new potential planets. But these need to be confirmed with follow-up observations. And so one way that we can help do that with EV scopes is, we have these telescopes that are, we have thousands of them now. So we have many opportunities to observe the largest of these planets and see, there's if you point at this one star, it's predicted that there's a planet there. Look at this time and observe the star for this amount of time, maybe a few hours, and see if you see this transit. And we can then kind of take the burden off the other telescopes that are bigger and their time is more expensive. That we can kind of take the burden off them so they can go follow up other planets, maybe say Earth-like planets that are smaller and harder to detect, but kind of arguably maybe more interesting because they're Earth-like. Maybe they're closer to where we might want to look for life, something like that. So we're kind of we're doing our part, chipping in with the EV scopes.
So thinking about what we're doing with the EV scopes, what do you hope that we learn or accomplish in the year ahead? I guess both as an astronomy community at large, but also as part of the SETI and Unistellar team.
Yeah, so it kind of goes back a little bit briefly to why we study exoplanets in general. So one of the things I mentioned was putting the solar system in context. So, is our solar system typical or not? We have 4 small rocky planets close to the sun, and then 4 larger gas giant planets farther away. Is that common or not? So we want to keep finding, as a community in astronomy, the exoplanet community, we want to keep finding examples of exoplanets and exoplanetary systems in order to help answer that question. Are we typical, or is our arrangement of planets extremely rare? And maybe that connects again to how life arose on Earth. So one thing I'd like to see is, TESS and other missions that are currently working right now keep finding new planets, particularly smaller planets, more Earth-like planets, and planets that are Earth-sized in their habitable zones, which means that they're just the right distance from their stars, that you have the right temperature and conditions to have something like liquid water on their surface, which we know can be conducive to life. So kind of as a community, I'm looking forward to finding more planets, especially more small planets. With the EV scopes, I hope we can help follow up more of those test candidates and help confirm that some of these planets that are potential planets are actually planets, not just some false positive signal. And then I guess just kind of in general, personally, for me, I hope that we kind of accomplish something that we haven't even thought of yet, because that means that we'll have done something new and exciting, and maybe something that no one's done before.
Well, I will keep my fingers crossed for us. Thank you so much, Tom. This was wonderful. We appreciate your time. And I'm going to say adieu so that we can be joined, or rejoined, I should say, by Val, because we were just talking about extremely rare events and, of course, gas giants, and these things come together for tonight's great Jupiter-Saturn conjunction, or what some people are calling a Christmas star, and Val is going to tell us a little bit about that. So those of us with clear skies this evening are going to witness a super rare planetary alignment, which has not been seen for almost 800 years, at least not by us Earthlings. So Val, what exactly is taking place this evening?
Yeah, so this evening is a rare celestial event. It's the last time that you mentioned, last time Saturn and Jupiter were this close and actually observable was 800 years ago in 1226. And actually the last time they were this close was in 400 years ago in 1623, but they weren't actually visible to the naked eye because it happened during the day. This particular event is known as a great conjunction, and that means that's when two celestial objects appear very close in the sky. But even though they appear very close in the sky, Jupiter and Saturn are actually about 456 million miles apart. So pretty far apart, but they appear very close in the sky.
And you'll be able to see it with your naked eye or a pair of binoculars. So this is kind of a binocular view, but even to the naked eye, starting really shortly. In fact, those of us on the East Coast, if you step out right now, you may be able to see it. Those on the West Coast just a little bit later. But I think that's what's pretty special about it, right? Is that you can see it with your naked eye and it's so bright and visible.
Yeah. So if you look about 45 minutes after sunset towards the southwest above the horizon, you should be able to see two bright objects in the sky that look like stars, and that's Saturn and Jupiter. Saturn will be the dimmer of the two, and Jupiter will be slightly above, or slightly below, sorry, and brighter. In binoculars, you should also be able to make out some of Jupiter's moons. The four largest moons of Jupiter, called the Galilean moons, Ganymede, Callisto, Europa, and Io. And you also should be able to make out Saturn's largest moon, Titan.
So can you tell us something? I think that Saturn and Jupiter, in my opinion, are the most beautiful objects that are kind of in our solar system. Just the color and the different features are spectacular. Anything interesting that you can share about Saturn and Jupiter with our viewers?
Yeah, sure. So Jupiter, as you might know, is the largest planet in our solar system. It's actually one of the brightest celestial objects in our night sky. I believe it's third largest after the Moon and Venus. So it's a gas giant planet, which means it's mostly hydrogen and helium. And it has 79 known moons, the largest of which are the Galilean moons, which I mentioned earlier. Jupiter is also the fastest spinning planet in our solar system, and it takes about 10 hours to spin once around its axis. Also, although they aren't visible to the naked eye, Jupiter has a faint ring system. I'll get into a bit about Saturn as well. So it's the second largest planet in our solar system. Like Jupiter, it's a gas giant planet. being made of mostly hydrogen and helium. And unlike Jupiter, it has one of the most magnificent ring systems in our solar system, which is made mostly of ice particles, but also rocky debris and dust. It has a persistent giant hexagonal jet stream around its north pole, which looks pretty crazy. It also has 82 known moons, some of which contain water, which may mean they have life. Saturn's largest moon, Titan, is fascinating for its thick atmosphere, rivers and seas of methane, complex hydrocarbons, and plastics on its surface. And underneath its surface, it also has liquid water.
I'm going to pull up here. We've actually gotten some gorgeous conjunction images from users around the world. I know that if you're like me, you may be a little bit disappointed by the clouds that are disrupting tonight's view. So why don't we go through and share with you some of these gorgeous images. Val, can you tell us, what are we looking at here? This is so that people can kind of get a sense for where these will be in the sky, right? Are we looking at constellations?
Yeah. So yeah, the center image has constellations. On the left side, you have the view of Saturn and Jupiter. Saturn's the fainter object above, and Jupiter's below. And on the farthest right image, you can actually make out a little bit of Saturn's rings. Oh, in this image, you can see some of the moons of Saturn and Jupiter, which is really cool. You can make it out with the EV scope. So if you see next to Jupiter, those dots are moons of Jupiter, and they're all like in a line because that's the plane of Jupiter and where its moons are. Yeah. It's the same image without labels. Yeah, and then this is really cool. This is an image from Lionel, and he's actually in the southern hemisphere at Reunion Island. So this is a view from the southern hemisphere of what he's able to see, Saturn and Jupiter and some of his moons.
So is that why that image was turned slightly differently? The perspective is different than this perspective from Belgium?
Yeah, exactly.
So here they are getting a little closer. And then this was taken just this past evening by an EV scope user in Japan. What are we looking at?
Yeah, so again, you're seeing Jupiter and Saturn and its moons. It's a really great image, well detailed. Yeah.
So head out shortly, grab a pair of binoculars if you have them, your EV scope if you have it. And here in North America, we'll be able to view it right now and into the early part of the evening. So we'll have even more images that we're going to be sharing from the conjunction later on. So please join us in about an hour and a half. So 7 p.m. Central, when we will be talking about nebulae. We'll be exploring more of our own Milky Way galaxy. We'll take you through even more of the Jupiter and Saturn conjunction images and observations. And we will also hear about whether or not there is life out there on Earth. Is there really a galactic federation, and where do we sign up? I'll be joined by Frank Marchese to give us the details. And then at the very end of our next session, we'll learn about who has won our Nickname the Asteroid contest. So thank you for everyone, the hundreds and hundreds of people I've noticed who joined us for this very first part of our Winter Solstice Virtual Star Party. Thank you for all of my co-presenters. Until I see you again later this evening, I wish you all clear skies.